right? Again, this is the same vector in TBS2. And we come now to Nabil's question. So again, I'm trying to stress the philosophy of the differential geometry. What these scientists try to do, like I said, they try to generalize the concept of surfaces in higher dimensional space. Okay? So we have surfaces, we can deal with surfaces in 3 dimensions, we are very good at visualization, but now if they live in very high dimensional space, we cannot visualize, we need an abstract way to deal with the surface. Or, it doesn't have to be a surface, as long as it abides by the definitions of the surface, the manifold, then we can deal with it, like SO3. Okay, so it's a generalization of the concept of a surface. Second, we don't want to resort to the fact that we live in high dimensional space. We need to do calculus on the manifold. And how are you going to do calculus on the manifold? Well, we said, since it can be flattened out, I can do all the calculus here. Use your coordinates and do the calculus here. So here comes the third point, or the third point in the philosophy of the course, which is, well, you're going to use a coordinate chart, and these coordinate charts are arbitrary. I can use something and you can use different thing. So whatever calculus you're going to do, whatever operation you're going to do, it must be independent of coordinates. And this is a very big deal, okay? It has to be independent of coordinates. So back to Nabil's question, this red thing, vector, written in one coordinate set, which is the stereographic projection, should be exactly equivalent to this vector written in the other coordinate set, okay? Which is an obvious requirement, but I have to stress it. Where is the pen? Yeah, here it is. Okay, so any operation you do with tangent vectors must be independent of your choice of the coordinates, okay? So this will lead us to what operation we will do, we usually do with vectors. Any questions so far? So we define the tangent space to be what? Just the set of velocities of curves, which is a very natural definition. If you have a curve on M, by definition it lives entirely on M, its velocity vector is tangent to it. That's it, okay? And this definition is intrinsic, doesn't have to do with an ambient space at all. You can do your work in ambient space like I did here in the blue thing, that's fine if you are allowed to. But sometimes if you cannot write in ambient space, we can do it in coordinates and get your vector in coordinates, but we want to make sure that these are equivalent. If you want to do any operation, we must get the same result, okay? So what do you mean by an operation? Let's have an example for an operation that we do with vectors. What operation? I mean, we are in differential geometry, so most of our focus will be on functions, differentiable functions on manifolds, right? We have a differentiable function on a manifold. So a vector, how a vector can act on function on M, differentiable function, smooth, C infinity. How? Let's say how. Doesn't have to be. Doesn't have to be just to. It doesn't have to be actually a manifold. Let's say this is C infinity. C infinity. Even in Rn, in your computation, how a vector acts on a function. But one way actually is the vector acts on the function. So V is a vector. V is a vector acting on a function. So V takes a function. Actually, this acting is linear, so you can write it like this as a multiplication. We can define one of the actions as, which is actually the typical action, as directional derivative. So V has components V1 up to Vn. So V1 partial f partial x1 plus yada yada Vn partial f partial xn. So in our language in Euclidean space, in our language this is nabla v dotted with, I'm sorry, this is nabla f dotted with v, right? Nabla f dotted with v. This is the directional derivative of f along v. Obviously, we don't want to do it this way because this is the Euclidean space way, right? We don't want to write, well, we will do a similar computation, like here. But we will not write it this way, because this way is not well defined. Why? Because nabla f by definition, I mean nabla f may be outside of the manifold. This dot product is not defined yet. We didn't have any, we didn't say that we can do dot product in the manifold yet. So how we can do this kind of thing on the manifold? Okay. So just for those of you who want to have a picture, if this is, my typical example, if this is an ocean, and if you have here contours for function, say temperature, this is temperature is 0, temperature is 10, temperature is 20 Celsius, right? And you have current V. If you have a particle now, and this is very familiar concept in fluid mechanics, if you have a particle that is flowing with the flow, with the current, this particle, it will feel more and more hot, right? How fast its temperature changes as it flows with that vector, temperature per second, this rate is exactly nabla f dot v, right? Okay. So, in this sense, V in TPM, V, a tangent vector to the manifold at the point P, actually can be viewed as a map that takes a function and gives you a real number. Okay? So I'm reminding you here, we said C0, 0, 1, this is continuous functions on the 0, 1 interval, right? So C1 is differentiable functions on this interval. C infinity is continuous functions on that interval. Likewise, I can say C infinity M, continuous, what did I say? Continuous functions, differentiable functions, infinitely differentiable, which we call smooth functions. Likewise, I can define smooth functions on M, right? So precisely, this is the set of any f that takes M and gives you a real number such that f is smooth. F is C infinity, okay? So this is on a side. So any vector now, any vector can be seen as a map from C infinity M that takes functions on M and gives you a real number, right? What is this map? It's just the directional derivative. So a vector can take a function. A vector can be viewed as an operator on functions. Takes a function and gives you back a real number. Any question about that? So let's have this. This actually motivates this definition. A derivation D on M at P is a map, actually linear map, that takes functions on M and gives you real number. So map that takes function and gives you real number. What did we call it in dynamics? Anybody remembers?
Functional.
Functional, very good. Okay. So we have this functional or whatever satisfying D takes a function, gives you a number, and it's defined only at a point P. So satisfying the following property, if it takes multiplication of two functions, it satisfies the following. So here f at p is just a number, right? Multiplied with d of g, f and g are functions, okay? D acting on g is a number, this guy is a number. Multiply them together, please, and we will add the other way around, which is g at p times d of f. Simply, it's the product rule, right? Which we call the Leibniz rule. So, as I said, the lecture on math was to stop expected why questions. This is like a derivative, right? That's right. This is a derivative, but let's extract what is the essential feature of, differentiating the function. What type of thing, what type of action that satisfies this guy? Well, just the derivative at a point. Get your function differentiated at a point, it perfectly satisfies this guy. Okay, so that concept we need to generalize it. So here is that concept we need to extract its essential feature. What's the essential feature? It's a linear map for the function. It takes the function, gives you a real number, satisfies this guy. Okay, now if you want to differentiate the function at a point, give me a number, it satisfies this guy.